So this video is going to cover the second part of the matter module of paper 1 physics exam, and this really is the heart of the topic. This is the most important sort of bit of the module overall, and the bit that is most frequently assessed. So to start with, we need to know the different state changes. So obviously this is reasonably straightforward. Going from a solid to a liquid is melting. Going from a liquid to solid is obviously freezing. So think of going from ice to water, which is melting, or water to ice. Liquid to gas is one that people frequently get wrong. That is boiling. Evaporation is actually something different, so please try to make sure you remember that. And condensing is obviously the opposite. You can, of course, also go directly from a solid to a gas and miss out on liquid state. That is called sublimation. These 5 phase changes are referenced specifically in the specification, so you must know them. The opposite of sublimation is deposition, so that's just for sort of completeness. And there are other states of matter, so for example like plasma, which is like what a flame is, and that is ionization. So that occurs when you continue to heat a gas to the point where the electrons boil off, and recombination being the opposite. But it's the ones that are highlighted in yellow that are the key ones you must know. And in all of these state changes, there is an increase in internal energy. So when we go from ice to water to water as a gas, then we are adding thermal energy to the system. If we go in reverse from steam to water to ice, we are removing thermal energy. So you should understand the different states of matter, and if not, make sure you've watched the previous video on here. And it's helpful at this point just to make a brief note about the different types of bonds that exist between and within particles. So when we talk about changing state, it is the intermolecular, the forces between the molecules that are the things that are breaking when we change state. We're not breaking chemical bonds when we change state because it's not a chemical reaction, it's a physical process, which we'll get to in a second. So it's important you understand that when temperature increases, eventually we will reach the melting point and boiling point, and that's the point where those intermolecular bonds are able to be broken because there's sufficient kinetic energy to overcome them. And that's the key sort of thing that has to happen. So I'll just pause the video and just read through this slide before moving on. So here's a quick question that you can just test yourself with. Which of the following accurately describes the changes in energy during melting? So when we change state, one important thing to note, which I should demonstrate in a moment, is the temperature doesn't change. There is no change in kinetic energy. When we change state, we are reorganizing and rearranging the particles. So there is a change in potential energy. The more spread out the particles, the higher the potential energy. So when we change state, in this case melting, internal energy is increasing. If we were freezing, then it would be in reverse. If we were freezing, internal energy would be decreasing and potential energy would be decreasing. So we've recapped on the previous video the difference between heat and temperature. It's included again here because it's important. So I'm taking a moment just to read and make sure you are familiar with both the differences of temperature and heat. So again, just expanding on this has been covered before, but it's highlighted again here because it's important. When we talk about internal energy, which is like the pseudonym for thermal energy, it's because particles have energy in 2 forms. They have energy as a result of their movement and their spacing. So kinetic energy, which is to do with the speed of the particles, that's linked directly to the temperature, whereas potential energy is linked to the spacing and the elastic potential, not the elastic potential energy, the intermolecular forces between the particles. So gases have higher potential energy than liquids and solids. And again, just to put this into context, this is the important bit now leading into changes of state, which is that when we are just increasing the temperature of an object, we're increasing the kinetic energy. When we're changing the state, we're not changing the temperature, we're just increasing the potential energy because we are breaking or making intermolecular forces, depending on which way you're going. So obviously what we're talking about here all the time, state changes are examples of physical changes. So you should know the difference between physical and chemical, and this again goes back to the idea of the bonds I just showed you. So physical changes is where there's no new substance being made, there's no chemical reaction taking place here. There's a change in appearance, but this is basically things like changes in state or dissolving. Okay, and the really important feature of physical changes is you can always get back the thing you started with, so they're reversible. So for example, I can freeze water into ice, but then I can also melt that ice back into water. Chemical changes involve a breaking of the chemical bonds, and therefore you form totally new substances, and they're irreversible. So, for example, you can't turn bread into toast and then back into bread again. There's a chemical reaction that's taken place, and it's almost impossible to kind of reverse that. So, whether there is a new substance and the reversibility is a really key distinction. So here are just some basic processes. Just have a moment just to think about each of these. I can pause the video and I'll just go for the answers. So obviously the key things you're looking for here is state changes or physical, chemical reactions. Like you can see there, the egg cooking, so the proteins changing shape, the fireworks, rusting, all chemical. The wood one sometimes catches people out because they sometimes go, well, it's not really reversible because you can't cut it. So you can't like put it back into like one piece log without glue or something like that. But the reason it's physical is not because it's not just about whether it's reversible. It's also, is there a new substance formed? And cutting it in half doesn't make any new substances. There's no chemical change there, so that's a physical change. Dissolving is the other really important physical change, and then obviously melting could also be physical, and obviously combustion is chemical. So this is unquestionably the most important slide in the whole of this section, and it's the most important part of the topic because it brings everything together. So this is an example of a heating curve. You can obviously have the opposite of this, which is a cooling curve, which is the same way. So you'll notice the arrows go both up and down on this. And so we've got here the different states of matter at different temperatures. So we've got solid, liquid, and gas. You can see the arrangement of those particles. That's obviously knowing the details about those states is the first thing that's covered. So then we talk about, okay, well, what happens when we're increasing the temperature? So in this section of the graph here, for example, where we're increasing the temperature, as we transfer thermal energy to the material, the kinetic energy of the particles is increasing, and that's why the temperature is increasing. So internal energy is increasing all of the time throughout this graph, but it's which bit of it is changing. So it's because kinetic energy is increasing. That part of the graph is linked to specific heat capacity because it's linked to a change in temperature. The plateaus of the graph, where the temperature is not changing, that is when you have a change of state, and that is an indication that you are no longer increasing the kinetic energy of the particles because the temperature is not changing. You're changing all of the energy going into the system is now being used to make or break those intermolecular forces, break those bonds between the particles, and the energy is therefore associated with latent heat, which is the energy required to change the state of 1 kilogram of substance without a change in temperature. So the very first plateau here, where you're melting and freezing, that would relate to the latent heat of fusion, which is the energy required to melt or freeze 1 kilogram, as opposed to the second plateau, which would be latent heat of vaporization, which is the amount of energy to boil or condense 1 kilogram of a substance. And so each, we recognize how the equations relate to those two sections of the graph. So if we think about thermal energy a little bit deeper, you'll be familiar with this idea that we talked about before about how thermal energy can be transferred from one store to another, but we can quantify this a little bit more. So this is all covered in the energy revision video, but feel free to pause it and just take a read of this so you're familiar with it. Because obviously the key factor here is specific heat capacity. So in this section of the spec, specific heat capacity is focused on from the perspective of the equation. So this is more like where you're going to get calculations. So in the first bit of the course, when you do matter, you look at specific heat capacity, but the practical of that. So I'm going to mention that again in a moment because it is important and is relevant, but I'm going to focus on the equation first. So please just take a moment just to pause the video and familiarise yourself with these keywords if you're not familiar with any of them at this point. So the definition of specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. Specific means divided by mass. Capacity is the ability to hold, and thermal energy is the heat induced. The key thing in this equation is that delta T is the change in temperature, so you've got to do the final, take away the initial to work out the overall change. And materials like water have a reasonably high specific heat capacity because they can store a lot of energy. Okay, so using the equation in sort of calculations, here's an example. I'm not going to pause each of these, have a go at them, and then obviously check your answers. So one thing you should absolutely get excited about in your exam is if you get to the heat capacity or specific latent heat, there is only one equation that has those things in it. So the moment you see that in your exam, get excited and just look at the equation on the data sheet and just immediately write E, M, C and delta T, because you know that's going to be the things that you've got to put into the equation. Obviously, if it's a version like this, you're just putting it in. The key thing is to make sure that your mass is appropriate, and then it's the change in temperature. Obviously, you'll get your final answer. A slightly trickier version of the question, so now we're doing specific heat capacity, same thing, there's only one equation with it, so I know what I'm going to start by writing down, but then I've obviously got to rearrange them. And the nice thing about when you rearrange this equation is obviously you've got E is equal to MC delta T as the basic version of it, but any other version of it is just energy divided by the other two things. So specific heat capacity is energy divided by mass times the change in temperature, which you can obviously then work through to give you for aluminium 908 joules per kilogram per degree C. This is an example of a question that's come up on the exam before, so you might have just a look at these. I'm just going to go through these really quickly, so pause the video if you want to have a look at them, and obviously the answers will invariably follow. And you can see how the mark scheme here is set out following the 4 steps, which is important as well. In this case, rearranging it to work out the mass. Thermal conductivity is linked to specific heat capacity because obviously the better the thermal conductor, the more heat can be transferred to and from the material, and that might therefore affect what the overall storage capacity of the material is. This is a particularly important question because this highlights the practical. So describe how a student could use the equipment to determine the specific heat capacity. Now I should say this is not the only version of the practical. So one key thing in this particular practical is we're using a joule meter to measure energy, but if you can't do that, you might have to work that out indirectly. So you might need to use a ammeter in series and a voltmeter in parallel alongside a timer in order to work out power by doing current times voltage and then multiply by the time to give you the energy. Then you need to always use balance to determine the mass that you're trying to work out the specific heat capacity for, and a thermometer for the change in temperature. So there is a maximum of 5 measurements that you must take: voltage, current, time, temperature and mass in order to work out specific heat capacity. And obviously you do that with a voltmeter, an ammeter, scales, a thermometer and a stopwatch. But you can use a joule meter to prevent you having to measure the time, the current and the voltage, which this version of the practical does. And then you obviously have to put it into the equation, which you've got each of those. Focus on things like measuring the initial temperature, final temperature. And if it's a liquid you're doing, think about like stirring it to make sure that it's evenly distributed. Again, there are some different examples here. This question about ways of improving the practical is worth just taking a moment to have a look at. Again, another version this time, but with the having to draw it from scratch, including the ammeter and voltmeter. And again, you can see how the marks were awarded in this example. There are lots of practice problems available to have a look at specific heat capacity on the revision PowerPoint, so I encourage you to have a look at that if you feel you need more work on it. Covering off latent heat, which is obviously when we're changing state, the first and key thing that we need to be mindful of here is our definition. So please be aware that there are 2 definitions for latent heat. One for latent heat of fusion, which is the amount of energy required to melt or freeze 1 kilogram of material, and latent heat of vaporization, which is to boil or condense. The equation, sometimes people will help remember this as the ELM equation. E is equal to LM, or ML, doesn't really matter, but obviously ELM spells out a word, so sometimes people like that as a way of remembering it. And if you're rearranging it to give you latent heat, which you can see here, it's energy divided by mass. So here's an example question. Again, please feel free to pause and have a go at this. Again, the key thing here is making sure mass is in kilograms, so routinely make sure that you get used to changing that. That's one of the most common mistakes. You don't need to obviously know any latent heat values, but very often what they'll do is they'll give you a table and you have to pick the right one for the right material. So like this example is for water. Here's another example, this time again for water in this particular case. But this is for latent heat of vaporization this time, so it's for boiling. So you might have to pick, is it fusion or is it vaporization? It might be for a different material altogether. And you can also link latent heat because mass is part of the equation to other equations in this topic like density. So here's an example that's slightly trickier, which might also encourage you to use standard form. So that would be an example of a sort of slightly harder question on this topic. Here are some other questions which are going to cover in the Vision PowerPoint. Feel free to pause and have a go at any of these. And I'm just going to pop the answers up again, please.